大家好，我是清华大学电机系黄衍介。Today we're going to talk about the electric field direction in the wave, and we call this direction polarization. In many applications, we need to know the electric field direction of the wave, and then we know how a wave can interact with charges in the material. To begin the discussion, I want to define a z-propagating plane wave so that we can simplify the discussion for polarization. Then I'm going to show you a simple polarization state, which is linear polarization. After talking about the linear polarization, we'll do some general analysis for a polarization state. And then finally, we're going to conclude this lecture with elliptical and circular polarizations. And as usual, we're going to have some review before we close this lecture. So the first session, we're going to talk about z-propagating plane wave. And this means that we're going to specify the propagation of the wave vector along z direction. So in the next lecture, the lecture 5, we have a general solution for a plane wave. And this is the phasor, the electric field for plane wave propagating along k direction. And this r is just the general position vector. And for this the general solution, the k has 3 directions, kx, ky, kz. And when we say that we want to see a wave propagating along z direction, we just set this k vector along z direction. So k dot r only has one term, that is k multiplying with z. With this specification, and we also know that for TEM wave, the electric field and magnetic field are going to be perpendicular to the wavefront direction, and k is along the wavefront direction. So we know that the electric field is going to be in the xy plane. So we have the freedom to choose the direction for the electric field in this plane. And again, to simplify the discussion, we simply define the direction of the electric field along x direction. So we write down the expression for the electric field like this. There's an amplitude associated with it, and then exponential minus jkz, and the direction of this electric field is along x direction. So we use this as a Gaussian solution and put it into Helmholtz equation, because whenever we deal with harmonic wave, we always start the analysis from this Helmholtz equation. And we know that the Laplacian operator will require you to do this 3 partial derivatives along x, along y, along z. But now you have a wave propagating along z direction, and it's a plane wave. So this means that there's no variation along x and y direction. Basically, when you propagate a wave along some direction, and on the wavefront for plane wave, you don't have any variations. So this means that with this definition, you can drop this partial derivative with respect to y and also with respect to z. So for these 3 terms, you only have to keep one term, that is the double derivative of Ex, the electric field along x direction, with respect to z. And then copy down this k0 square to here. And k, don't forget that this is a wave number for a wave, and it's expressed by the angular frequency multiplying with the square root of mu epsilon. And if you try to calculate out the final value, then this k0 is going to be equal to 2 pi over the wavelength. Now you have a trial solution like this. We just showed this on the last page. Electric field along x direction, and then you have a propagation constant k in this complex exponential. So you just put this into the Helmholtz equation, and then immediately through this double derivative with respect to z, you get k squared plus k0 squared equal to 0. And so quickly you have this result. K is going to be equal to plus minus K0. So this means that you can put this plus minus K0 into this expression, and this expression is one of the solutions to this Helmholtz equation. So the complete solution is going to be a superposition of these two terms. One with the minus jk0z on this exponential term, and then you have the jk0z on the second term. And last time when we talked about lecture 5, I already told you that the sign before this j, this imaginary unit, will tell you the propagation direction of the wave. And we're going to see this for this wave in a moment. So think about that you pick up this first term for your analysis, and we'll come back to this second term later. So to convert this phasor into a real expression, you simply multiply this with the exponential j omega t and take real part of it. And very quickly you can just write down this expression, because you combine this exponential minus jk0z and j omega t. When you take real part of it, you end up having this cosine function. And when you take this magnitude for this coefficient, then you come up with this phase term, phi plus. And if you want to see this wave in motion, we also talk about the propagation of the wavefront before. Basically, you just set the phase to be a constant value, and then see how this phase will change over time, over space. So now, if you write down this phase to be a constant value, and then do a spatial derivative with respect to t, with respect to time, then it's going to tell you the speed of this wave propagating along z direction. And it turns out that you get a constant value that is the speed of this wave in vacuum if you use the vacuum permittivity and also vacuum permeability for your calculation. And this calculation gives you a positive value. This means that this solution gives you a wave propagating along plus z direction. So the sign preceding this j tells you the direction of the propagation of the wavefront. And once you have the electric field, then you can calculate the magnetic field through this solution we derived in lecture 5. So if you just put this z direction propagating wave with a polarization electric field direction along x direction, then you know that's an, that is the wavefront propagation direction along z, which is az right here, and the electric field is along x direction. So this cross product is going to give you a unit vector along y direction, and the magnitude of it is going to be equal to 1 over intrinsic impedance multiplying with the amplitude of the electric field. So this is the final result for the phasor of the magnetic field. And now we can construct the directions for the electric field and magnetic field with respect to the wavefront direction. So electric field starts with the direction along x direction, and we just derived the magnetic field along y direction, and the propagation direction of the wavefront is along z direction. And you can also convert the phasor field into a real field. So you just multiply this result with exponential j omega t and take real part of it to get this final real solution for the magnetic field. Well, this calculation tells you one thing. If you know the propagation direction of the wave, and if you also know the direction of the electric field, then the magnetic field is also fixed from this calculation. So in general, you don't have to specify both directions of the electric field and magnetic field. As long as you know the direction of the electric field and also the propagation direction of the wavefront, then the magnetic field is already known. So when we talk about polarization, we talk about the direction of the electric field and also the direction of the propagation. We don't specify the direction of the magnetic field because it's already fixed if we fix this direction and also this direction. Now, let's look into the second term, and you expect that the analysis is going to be quite similar to the analysis for the first term. For the second term, again, you can convert this second term into a real expression by multiplying this first term with exponential j omega t and take real part of it. Then you can end up with this solution with an amplitude and then a cosine function. And inside this cosine function, you have omega t plus k0z plus the phase of this amplitude of the complex amplitude of the electric field. And be careful that because you have plus sign here, so you have a plus sign here, and these two plus signs are consistent to each other. And again, if you want to see the wave in motion, you set the phase of this cosine function to be a constant, and you can take derivative of the z with respect to time. So you can start to see the wave in motion. And turn out that this constant phase gives you a phase velocity in the minus z direction. You see there's a minus sign here, but you are taking derivative of z with respect to time. So this minus sign tells you the propagation direction of the wavefront in the backward direction, in the backward z direction. And similarly, you can also use the solution of the electric field to calculate the magnetic field by using this formula we derived in lecture 5. And the result for the phasor field is just like this. But this time, this AN is along minus z direction, and this electric field still along x direction. So the cross product is going to give you a direction along minus y direction. So for this minus z propagating wave, you have electric field along vertical direction x, and then H field, magnetic field along minus y direction, and the wavefront propagation direction is along minus z direction. And by using this phasor field, you can also convert it into a real solution. And so you see this proportional factor that is equal to 1 over intrinsic impedance. And there's a minus sign in front of the whole thing, telling you that this magnetic field is along minus y direction. And so if I want to plot a three-dimensional illustration, then the electric field is along this direction, varying sinusoidally, and the magnetic field is along minus y direction, and the whole pattern propagates along minus z direction. So in this section, we more or less understand the physics and also expressions for the field for a z propagating plane wave. And we talk about there are two possible solutions. One is along plus z direction. The other is along minus z direction. And for time-varying electric and magnetic field, they propagate as a wave governed by the wave equation. If we talk about time harmonic waves, then we can start the analysis from the Helmholtz equation. And for TEM wave, transverse electromagnetic wave, the electric field, magnetic field, and wavefront vector are perpendicular to each other. And for example, if you just point your 4 fingers of your right hand to the electric field direction and rotate it about the toward the magnetic field direction, then the direction of your thumb is going to be along the wavefront propagation direction. So this is one way you can figure out the directional relationship among the electric field, magnetic field, and also the K vector. And we also talk about a Z propagating electromagnetic plane wave has its electric field and magnetic field along XY plane. So in the next sessions, we'll be talking about the polarization of the wave, and the polarization of the wave is going to be on the XY plane. So this will simplify our discussion. Thank you.